Okay, can you see it now?
Yeah.
Yeah. Okay, should I start?
Yeah.
Yeah, okay. So today I will continue talking about the properties of problems with quench randomness. So I talked about heterogeneity, I talked about frustration yesterday. Uh, I'm going to discuss now what is called the property of self-averageness. So let me say with simple words what this means. Imagine that you have a problem with interactions which are drawn from a probability distribution, as I was discussing in the case of spin glasses. And imagine that uh, if each sample prepared in an equivalent way will have different realizations of these interactions between the magnetic impurities. If each sample were behaving differently from the other ones, well, the problem would not be very interesting because it would be too complicated, no? And too peculiar to each sample. One should, write a model for each sample and solve this particular model with this particular set of interactions to describe the sample. But actually, this self-averageness property is saving us from this, impossibility of making the problem interesting from a theoretical point of view, because actually, in the limit of a large number of degrees of freedom, the behavior of all of these samples prepared in equivalent ways and for typical realizations of the interactions between the impurities behave in the same way. So if one wants to put this statement in more mathematical terms, what I'm meaning is that the disordered induced free energy density uh, is distributed, okay? Because since the couplings come from a probability distribution, the free energy that we will compute for each of these couplings is also distributed with some probability distribution induced by the couplings. But in the limit of large n, the distribution of the free energy densities approaches a Gaussian with a vanishing dispersion in the thermodynamic limit. So it's concentrated on some value, on some function of the control parameters, which is the temperature over some energy scale. Uh, and this is the statement that appears here, like limit of n going to infinity of the free energy density, which depends on the system size, of beta j. Here I should have written beta j. So I'm writing things now that I have to correct in my transparencies. Averaging. So in the limit, I should have written that f infinity is a function of beta j. And what I mean by independently of disorder is that, for once I have chosen the probability distribution of the couplings and I'm working with that one, okay, this f will be just a value, a function of beta j, but not dependent on the details of the probability distribution for typical realizations of disorder. So why do I say typical realizations of disorder? Because even if I take a probability distribution for the JIJs, which, for example, could be say box form in between two values -1 and 1. So, okay, this has average 0, which usually average of disorder is written with an overline, or in my slides, I will write it with the square brackets. So this distribution has average 0 and has some variance, let me call it j squared, that you can compute easily with this distribution. So when you draw the JIJs from this kind of distribution, you will have different values of the JIJs with positive and negative values. But just, it's possible, though not very probable in the larger limit, to pick JIJs which are all positive. This is possible, but it's rare. To pick them all from this little interval here is rare. So this is not typical. typical is, to have as many positive as negative values, and then, even for this particular choice of the JIJs, have average 0. So when I say typical, this is what I mean. So for all typical JIJs, then you will have that the limit of the probability distribution of the free energy density induced by those JIJs will reach a limit, which is given by this expression F infinity of beta J. So this means that experimentally all typical samples behave in the same way. If by bad luck you draw a sample which is with all the JIJs positive, then you don't have a system with frustration. You have a ferromagnet with some disorder. And this sample will behave differently from the typical ones, of course. But this I'm excluding because the probability to making a sample like this one in the largest limit is very small. Now, in theory, in theoretical approaches, the advantage of having this self-averageness property is that instead of working with the problem with one realization of the JIJs, one will work with averages over the quench randomness, because since all of them behave in roughly the same way, I can average over all of them and see then what happens with the average over the disorder of the quantities of interest. And in theory, it turns out that it's easier to work with averages over the disorder than to work with single samples. Actually, it's easier depending on what you want to compute, but in certain calculations, like when applying replica theory or when applying dynamic mean field theory sort of approaches, it's easier to work with averages over disorder than to work with a fixed choice of the random couplings. So in other words, what I'm saying is that these F infinity of beta J is also going to be equivalent to the average over disorder of the beta infinity of beta J. And this is what I'm writing here on the right-hand side. And note that the average over disorder of the free energy implies computing an average over disorder of the logarithm of the partition function. And okay, this is the difficulty of having to average a logarithm makes the necessity of to use methods which are a little bit uncommon. And this typical method that is used is this replica theory to rewrite the logarithm as a Taylor expansion of this ratio between z to the power little n minus 1 over little n. And okay, then with this transformation of the log into this power of the partition functions makes the calculation feasible. But I'm not going to discuss replica theory because it would take me too long to do it. But I just wanted to flash here, which is the idea behind, going from the problems at a fixed realization of the random couplings towards the problem with an average over the random couplings, and then the application of this trick that makes the calculation of the average of a log feasible. Okay, so let me go back to this self-averageness property and give some examples of how can one see this at work and prove it in certain cases. So I say again, take two samples with different realizations of the random couplings, so different interaction strengths, JJ, so if you have random fields, different random fields, drawn from the same kind of probability distribution. So what do I mean by different kinds of probability distribution? I had this box distribution here, but I could also have a Gaussian probability distribution with the same zero mean and the same variance. So these are the different kinds, the same, but this is what I mean by different kinds. This is a different probability distribution than that one, but has the same properties of having zero mean and having the same variance, okay? So I not necessarily have to draw the interactions from exactly the same probability distribution. I can even, enlarge a little bit the possibilities of probability distributions and still have the same global properties of my system. So the question is their behavior going to be totally different? And the answer will be no in the long n limit, in the larger limit. And but no, depending on the quantity you want to look at. Okay, there are certain quantities that will be self-averaging and certain quantities which will not be. Typically, the interesting quantities are, and then okay, we're happy with that. But I have to, stress the fact that you can try to measure something which will depend on the particularization of disorder or will depend on the kind of probability distribution that you use to draw the couplings. So let me give examples where this will be clearer. Concerning the observables, okay, before going into this thing, let me give examples that will be more clear, I think. So take the disorder Ising chain. So you put Ising spins on a line, on a lattice, one-dimensional lattice, and you draw the couplings between those spins from a probability distribution. So this notation is convenient. It just, label the spins by their position on the lattice. They are coupled via nearest neighbors couplings only. So this is why Si plus 1 appears in this energy. I sum over all the sides. And the couplings I also label by the first side over which the coupling is acting. So this is the JIs. I don't need to put JIJ. I just put I here because it's ordered. Okay, so now I can compute the partition function for this one-dimensional Ising model by simply changing variables in the partition sum, going from these pairs Si plus 1 to the auxiliary variable or change of variables sigma i's, which is also an Ising value, a bimodal variable of Ising kind, because I can have Si plus 1 plus, and then I have, if both are plus, sigma I is plus. If both are minus, sigma I is also minus. If sigma I is plus, sigma I plus 1 is minus, then I have minus 1, minus 1. Okay, so you can see that sigma I is also a b-valued variable of Ising type. So this is what I'm doing here, changing variables. And now, of course, I can do this partition sum, and I get this twice cotangent of beta ji. So you see that z is a random variable because the ji's are random variables. Moreover, it is a random variable built as the product of n random variables of IID kind, so identically independent, identically distributed random variables, random numbers, and this is what is z. But now if I take the log to compute the free energy, I transform the product into a sum. And if I have a sum of random variables which are IIDs in the larger limit, I can use the central limit theorem to say something about the distribution of this f, right? So I go back here. This is the result if I now normalize by n, the number of variables in the problem. So I have a normalized random number. And using the central limit theorem, which I recall that if you build an x, which is 1 over n, sum over xi's, this capital X will be Gaussian distributed with average equal to the average of the xi's, and variance equal to, well, the variance of the xi's, normalized in this way with n. So you see that they are the properties of the mean and the variance of the distribution of the ji's, which is determining which is the mean and which is the variance of the capital X. So therefore, the free energy density is a Gaussian distributed object, and its variance vanishes when n goes to infinity, you see, because I have this normalization by n, which appears here in the variance. And moreover, the typical value, so this Gaussian distribution is Gaussian distribution has a maximum. So this is what determines which is the typical value that you will draw if you draw this Gaussian variable many times. So this typical value is equal to the average for Gaussian distributed random variables, right? So in the larger limit, I am proving for this model very simply that the free energy density is a self-averaging object with this property of typical equal to average. You see that for the partition function, this doesn't hold, right? Because the partition function is the product of random variables, but the free energy, because of taking the log, has this property of being amenable to central limit arguments, and then the self-average is a property that holds. Now, okay, this was the one-dimensional random missing chain, very simple problem, but not that interesting. Now, what happens in problems with the defined in higher dimensional spaces? So in higher dimensional spaces, you cannot do the exact calculation I have just done, but you can make an argument, which is the following one. So you pick your sample and you say that you're going to break it in pieces. Okay, so imagine that this is my two-dimensional cube or square where I have my sample. Can make it in higher dimensions. You divide it in pieces, which are sketched here with these black boxes. Okay, so if the interactions between your variables are short-ranged, so if you don't have interactions between this box here and that box there, or this box here and this box there, and this box here and that box there, the interactions are only concentrated on the interfaces between the box concerned, what you can do is you can say, well, the total energy of my problem will be equal to the energy of the bulks, so the interior part of these boxes, plus the energies of the interactions between the boxes. But if interactions are short range, I can neglect interactions between far away boxes. I can focus only on interactions between neighboring boxes. And moreover, I'm going to assume that since the space occupied by the interfaces between the boxes is a surface, while the bulks scale as a volume, then there are many more spins within the volume than on the surface. I will drop the contribution to the total energy coming from the surfaces. And in the end, doing this assumption, what you have is that, again, the free energy of the whole system, you can write as a sum, actually two sums, a sum over the boxes, which is this sum over here, of the free energy within each of these boxes that, in a sense, become independent with this argument. Okay, this of course is not exact, it's an approximation, can only be true in a large system size limit in which this capital L, which is the system size, and this calligraphic L, which is the size of the boxes, are both very large. Also, you need to have this calligraphic L to be very large to be sure that the surface to volume ratio of each of these boxes, is decreasing. It's decreasing in the large end limit, so it's negligible in the larger limit. So once you have done this, you see you have sort of gone back to the problem of the one-dimensional Ising chain, where you have a sum of random variables for your free energy density. These are the random variables. So this is the free energy, this is the partition function within the bulks. And you have the log. So here you have a sum of random variables. And then you use again central limit theorem. And you argue in this way that typical is equal to average. But I insist upon the fact that here there's assumption of short range interactions. And there is assumption of large system size limit that is used, and this is an approximation. But okay, this is the sort of approximations that can be made very precise mathematically and controlled, all these limits and so on. So this is a proof which is accepted with no difficulty by even the mathematical community.
Leticia, I had one question.
Yes, please.
Are you then replacing for each box by the Anneal free energy corresponding to the average J that you have for each small boxes?
No. In each boxes, I treat the partition function exactly. So this is the partition function within the box, and I'm not needing to change by an average. So this is a random variable which I don't know, but I know that the
Yes, but in that box, is J still fluctuating, or
yes, it is. It is. Yes. Yeah. The only assumption that you need to do is you have to drop all surface or interface contributions. So this you have to do. And for that you need short range interactions. Otherwise you cannot
then for
do it.
inside each boxes, you are still doing then a quench average for the free energies?
I'm not doing any average. I'm
Ah,
just saying that the Z, which is here, is a random variable induced by the J's within the box.
okay, I see.
Yeah,
Okay,
I'm not averaging. Yeah.
okay, thanks.
Mm. Um, so of course, this kind of proof doesn't apply to problems with long-range interactions. And the kind of models that we know how to solve have long-range interactions. So in principle, one is not allowed to assume self-averageness for problems with long-range interactions. But okay, mathematical people are able to prove it in a completely different way. And I'm not going to discuss it. If you want, I can search for references, and if people are interested, I can send references later on. But we assume that for mean field problems, fully connected systems, defined on complete graphs and so on, the self-averageness properties are applied. Um, so something else that can be said is that the annealed average was mentioned. So what is it, the annealed average? The annealed average corresponds to say, okay, I'm not going to average the free energy, but I'm going to average the partition function and then take the log. So this is another procedure, which is a procedure for which you don't have any proof of self-averageness because the z is not self-averaging. So this average of z doesn't represent the typical value of z. I don't know what it represents, but imagine that you compute that. So it can be proven, using Jensen's inequality applied to a convex function, that this annealed free energy is smaller. I mean, this is, yes, this, sorry, if I put the minus on the other side. So, okay, that there is this inequality. To say it in words is difficult. So there is this inequality between the two objects I'm constructing. And for the free energy, this is the inequality that one deduces from this inequality between the logs. So there are certain cases in which the anneal calculation, which cannot be taken to be exact always, however, in certain cases, it represents the good free energy density or free energy computed with the quench procedure, while in other cases it doesn't. And rather typically what happens is that at very high temperatures for the disorder configurations and situations, then these two objects are the same because you have a smaller or equal, so it could be equal, while in other phases this is not the case. So I will answer the questions in the chat when I finish with this discussion here. Finish with this discussion here. So something I forgot to say, I had it in the transparencies, but somehow I erased it. I am sorry for having done it, is that I said that certain observables enjoy these self-averageness properties and others don't. So this can be very easily seen within the example of the disorder ising chain. Imagine that within the disorder ising chain, you want to compute the correlation function between two spins. So let me do it in that. So imagine that you want to compute what I was calling C, correlation function between two spins sitting at sides Ri, Rj. Actually, I don't need the arrows because I am in one dimension. And this correlation function is Si, Sj, where the distance between these two is equal to what I call Rij above. So I have my chain. let's do the modulus. I have an I have a j side, and I have a distance Rij between these two spins that I want to correlate. So I propose to the students to write the expression of this correlation function and see that this correlation function actually depends on all the couplings that you have between these two sides or two spins that you want to correlate. So by this I mean that this object is a function of the ji, which is here, say the jk, which is there, the jl, which is here, the jm, and the jn that appear in this interval. So my previous notation, this would be ji plus 1, ji plus 2, ji plus 3, ji plus 4, in between these two extreme values. And you see, well, you will see you will see that you cannot say anything particular about this function that you will get here. You cannot get rid of these Jijs, which are in the middle of these two sides that you want to correlate. So this correlation function depends on the couplings, and well, for different realizations of the coupling, you will get different expressions for the correlation function. Let me close the door because there's a lot of noise here. So this you can do as an exercise. Okay, it's very, very simple.
But wouldn't you do self-averaging over this correlation functions? Like you would get a correlation function from your self-averaged free energy density. Wouldn't that the same thing?
It doesn't represent the actual correlation function between the spins. So you would get a wrong result for the correlation function if you proceed in that way.
Okay.
Yeah. Okay, let me have a look at the chat.
Ma'am, if I and J were really far apart, would that be the same?
No, because you will have products of J's. You will see that, so you have to take some logs to be able to use the central limit theorem. So, or otherwise you can have a distribution, but linked to products of, random variables, but not to sums. So, yeah. So first question is dispersion like variance? Yes, it is. So I never remember if in dispersion there is the square root or there is no square root. So the variance is this, what I was writing before, of a random variable. Sorry. So this is what I'm calling the variance, and this is the notation of sigma squared that I was using. So dispersion, I don't remember if it's, I think it is with, taking the square root of this, so it would be sigma. Should the sum over bulk be outside of the log? No, it's within. So you will do it carefully yourself. So it's because you take the log of the z, and then is the c that you separate in pieces. Okay, so yeah. I have a technical question. Isn't it rather the law of large numbers than the central limit theorem that you use there? Your final answer seems to be a deterministic number and not a Gaussian random number. Okay, let me move this here. Okay, so here is what you have. So what? Law of large numbers and central limit theorems come together, right? So there's a very similar kind of it's the same setting in a sense. So what you can prove with the central limit theorem is that this object, which has the same form as this object here, as the sum of random numbers, is Gaussian distributed. Okay, so this is the content of the central limit theorem. And moreover, the central limit theorem, it tells you which is the average and which is the variance of this Gaussian distribution. Concerning your final answer seems to be a deterministic number and not the Gaussian random number. No, my final answer is a Gaussian random number. So this object here is a Gaussian random number, and what the central limit theorem is telling me is which is its distribution. So this object is distributed still, Gaussian distributed, and the n appearing below this sigma square is telling me that for larger and larger systems, what this is telling me is that if I have a small system, I will get a distribution of this Fj that will look very wide. For a larger system, I will get something more peaked. And for an even larger system, I will get something even more peaked, and so on and so forth. And it's this scale here that is going like 1 over n. That is going down.
So maybe I can specify my question.
Yes.
So the question was, or that I had in mind was that you actually, yes, for finite n, yes, you use something like the central limit theorem, where I think if you scaled, by square root n instead, you would get a Gaussian random number with a variance that does not depend on n. But if you scale with n, you in the limit of n going to infinity, you get a deterministic number, right?
Because in the n going to infinity limit, exactly, you have only one value. Yes, in the n going to infinity limit, yes, this Gaussian goes so peaked that you have only the typical result, which is also the average. So Fj tip, which is also Fj average. Yes, in this sense, you are right. Yes.
Okay, thank you.
Yeah. Okay. By long range interactions, do you mean the interactions range scales with system size? Yes and no. It could be, or it could be even, long range interactions in the sense of decaying with a power law of distance, but with a power which is not very large. So, for example, the kind of models that we know how to solve, which are these mean field problems. Let me move a little bit so that I have. So I will talk about these models later today, but these fully connected models that I was introducing yesterday, where you have all the possible, well, okay, I'm missing some lines probably, all the possible connections. These, you see, there is no notion of distance here, so I cannot claim that I will cut the system in pieces. I cannot claim I can do something like this, because there are connections between all the sites in the problem. So this is one type of long-range interaction, because everybody is connected to everybody else. But you could also have interactions of the kind V of I Rij proportional to Rij to some power, which, okay, usually it's called sigma, or alpha, let's call it alpha. So if alpha is small, and this depends on dimension, what small means, then if the interactions don't decay fast enough, alpha small means that you have, I don't know, some decay of V of R which is rather slow. Then you cannot cut the system in pieces either, because you will have interactions propagating far away, and I cannot cut the system in boxes. So it's either one case or the other one. What is annealed here? Well, annealed is, again, another way of using these words, is averaging the Z and not averaging the free energy. So you average first the Z over the disorder, then you take the log and you construct this annealed free energy. It's a definition.
Physically, what would that mean? In a sense, why do you take the average first?
Because it's easier to compute. So it's not that, it's an approximation that sometimes is applied, because it's much easier to compute the average of the partition function than to compute the average of the log. To compute the average of the log, you have to go through this replica trick, while the average of the partition function is just very simple to do.
Thanks.
Is it right to say that any quantity, I don't know why this is so small that I cannot even read it. Is it right to say that any quantity observable that can be self-averaged should be in the form of sum of IIDs? Well, yes. I mean, I don't know if it's necessary, but certainly if you have sum of IIDs, then you can prove easily that it's self-averaged in large and limit. If not, can something like this be said about observables which can be self-averaged? Is right to say? Well, I would say that, if you have IIDs and you sum over them, you're sure that these things will be self-averaging. If not, well, you have to see case by case and try to prove it in another much more complicated way. This is just what I would say. Okay, so
yeah, hi.
hi.
So this question is connected to what Trideep was asking already. Is there any sense we can think of correlators for these systems, like averaged over all the samples? They don't make sense at all.
I don't think I understood the question. So can you say
so
it again?
Is there any meaning for like correlators in these systems, because they are sample dependent? By doing average over the samples, like we get some quantity. Does it make sense? Like as a
yes. Because I gave you the example of the one-dimensional Ising chain where you have all these J's. I told you to do to find the expression and see that you cannot self-average those. But in other systems, for higher dimensional ones, and you can check that the correlations are self-averaging. So you can do it, for example, numerically very easily. So you compute a correlation function for a given typical realization of the JIJs. You compute the average over many of them, and you see that in the large and limit they coincide. So it's not that for all systems which went randomness, the correlations depend explicitly on the realization of the random interactions. I should have said it. In high dimensions, this is not the case.
So in that sense, like I can simply compute correlators by taking this quenched average of the free energy and taking derivatives with respect to the source.
Yes, indeed. Yes.
Thanks.
Yeah, because otherwise it would be, as I was saying beforehand, it could be a problem, just no hope to say something generic about them, no? If it would depend on each particular realization of this sort. Okay.
So typically we expect them to become translation invariant and such, right? Okay.
In space, yes. Not in time. So that I will discuss later with the experiments. Okay, so which are the methods, theoretical methods, analytical methods that we use to try to deal with these problems? If we try to understand equilibrium properties, there are two favorite methods which are applied to problems which are defined on the complete graph, on the fully connected cases, which are these TAP for Thouless, Anderson, and Palmer method, which I will explain, which is basically an extension of the Ginzburg-Landau way of thinking. And it's a method that allows to induce and deduce, and draw free energy landscapes and see that they are complex with many more metastable states and complicated structure than in the Ginzburg-Landau problem. So this is what I'm going to explain later. There is also the replica theory. I will not explain it, it would take too long. And those apply basically to fully connected problems defined on complete graphs. Then there are methods which are a little bit more recent and that are specifically well adapted to deal with problems defined on random graphs. So these are the methods that people use in optimization problems in particular, because those are typically defined on random graphs, dilute ones, I mean, not completely connected. And then there are the methods which are specific of finite dimensional systems, so 3-dimensional, 2-dimensional problems, which go under the name of droplet theory, droplet arguments, or fractional RGs, but I will not tell you about them. I just wanted to mention them. And then we'll come to dynamics. You want to know time dependencies, because this is what is observed experimentally. Experimentally, the systems don't reach equilibrium. So then you have to deal with the time evolution and say something about that. And for doing calculations for the relaxation of these disorder problems, one uses generating functional techniques. Those go under the name of Martin Rose, Jans and the Dominicis methods. Derives Schringer, well, for the quantum problem is Schringer-Keldysh, the technical name, or closed time path integral methods. They're very similar to the classical ones, actually, if not almost identical. And from those generating functionals, you can derive equations, which I'll show you, not derive them, because again, it would take too long to do it, but equations which couple correlation functions, linear response functions, like the ones I discussed yesterday, and that can be solved, and that tell you about the dynamic evolution of these problems. These methods are completely solvable for the problems defined on the fully connected graphs. They can be extended in certain ways for the dilute problems as well, but they are certainly not, finite dimensions is beyond any hope of being treatable in an exact way. And once you have these generating functionals, okay, you can do the usual tricks of theoretical physics, perturbation theory, although it fails. Try to apply randomization group techniques when you look at the critical points, or do self-consistent approximations with which you derive these equations for the correlations and the linear responses. So I will then start talking about these TAP methods, and then go towards the dynamics and tell you something about the dynamics. Okay, Staules, Anderson, and Ball. So the first thing that we have to go back to before trying to extend the Ginzburg-Landau approach to these random problems is, go back and think about the properties I discussed. So I talked about spatial inhomogeneity. Not all sites behave in the same way. Given a realization of the random couplings, there could be regions which are more ferromagnetically coupled, regions which are more antiferromagnetically coupled, regions which are not coupled at all. So in space, even if your problems are completely connected, it could be that certain sites have interactions of one kind with the other ones, and then other sites have mostly interactions of another kind with the other ones. So spatial inhomogeneity is also present in fully connected modes. There was frustration, there was annealed and quenched. We are going to be interested in quenched. And there was this self-averageness property. So for this TAP method, what one does is one works at fixed couplings, fixed realization of the couplings. Doesn't do an average over the random couplings. One takes a typical realization of the couplings, works with that one, and claims that all the other ones will be very similar in the large N limit. So if all sites can behave differently, there is no reason to think that there's going to be a global order parameter describing the behavior of the problem, like there is in ferromagnetic phase transitions, as the ones that I was discussing yesterday. So in a ferromagnet in equilibrium, at temperatures T smaller than Tc, the average over the equilibrium distribution of any site is equal to the magnetization density. So there is an independence of the site index here in the result of this equilibrium average that you have in ferromagnets in equilibrium. So it could be plus or minus m, but this is for all i's. Now, if, again, in a ferromagnet, let me pick the case of a ferromagnet to let you next think about the more complex case. If one were to follow the time evolution of each spin in one of the two equilibrium states, so I pick one, I take time averages, I will see that the time average is the magnetization density in equilibrium plus some fluctuation. And this fluctuation is small with respect to the value of the magnetization density in equilibrium. And okay, the overline is the definition of time average that I have already discussed in the first lectures. So in the course of time, the time average of any site, say that I'm in the positively magnetized equilibrium state, will look like something like this. In a spin glass in equilibrium at temperatures T smaller than its typical, critical temperature, one expects each of the spins to have some average, but this average will depend on the site because, as I said, certain sites could be more ferromagnetically coupled, other ones could be more antiferromagnetically coupled, and so on and so forth. So there is no reason to assume in a spin class that all the SIs are going to be the same. So what TAP did is to say, okay, let me say that there is an average of equilibrium on each side, which is equal to an MI, which will depend on temperature. I should have introduced here temperature over J. J, what is J? Is the typical, is the energy scale associated to the variance of the coupling strength. Okay. So it turns out, it will turn out that in spin glass problems, there may be many different ensembles of these MIs that are equilibrium states or metastable states. So there will be a degeneracy similar to what we saw in frustrated magnets for the ground states of the antiferromagnet on the triangular lattice that I was discussing yesterday. But not only for the ground state level here, there will be these degeneracies, even for higher lying states in the free energy landscape. So what I mean by this is that what we are going to try to do is to extend this Ginzburg-Landau for paramagnetic ferromagnetic transition, which was just, well described by a global for the parameter with a change in this free energy landscape, going from having just one minimum to having two minima when going through TC, to a situation where in the horizontal axis you cannot have only one global order parameter, but you need to consider n other parameters. So this is a very large dimensional substrate on which I will build my free energy density, made by all these MIs. And here On top of this, there will be a landscape which will be complex. We'll have a lot of structure. So we will, below some critical temperature, it will start having, lots of minima, maxima. It's difficult to draw, but something like that. Okay, so this is what TAP shows with their construction.
In this case, you have the interaction strength also. Could it be just ferromagnetic and fluctuating around it, or you are choosing only the ones with average mean to be 0 case?
Interaction
strengths?
Yeah. So the interaction strengths are the JIJs, right?
Yes.
So for a typical choice of the ensemble of JIJs, where you have positive and negative JIJs, because typically you will pick as many as positive or negative sign, then you will have something like this. So for any typical JIJ, below some temperature, you will have something like that.
Okay, but if I take a JIJ whose mean is non-zero and fluctuating, will the scenario still be valid?
Yes, they will still be valid, but there will be some lower line state here, which corresponds to the ferromagnetic state.
I see, okay.
So that would be the ferromagnetic state, and then there will be also all sorts of complex.
And in your case, there will not be one global minima.
No, there will not be one global minimum because I'm putting the average to 0, yes.
Okay, I have one more question. So when you are defining this coarse grain magnetization, you're defining again on some length scale. Does it compare with correlation of your noise of the J somehow? Correlation length?
Here I'm working really locally, spin by spin.
These MIs are even side by side, not
side by side. I'm not doing any coarse grain. Yes.
Okay. Okay. Thanks.
Yeah, you're welcome. So, what is the meaning of these MIs from the point of view of an experimental person who will set his spin glass in equilibrium? And then, it's like the image I wrote before for the ferromagnetic problem, but extended to having many different values of MIs, MJs, and so on. So in the course of time, you will have an average, a local average of the magnetization, which is, say, non-zero, and, or it could be negative or positive, but okay, some value. And there will be fluctuations around that value. And when you average over time, you wash out all these fluctuations and you get values MJ of t, which don't fluctuate anymore. And you have these constant values which correspond to the MJs and Ks and so on. Okay, so this is because of the spatial inhomogeneity that I have to take care of all these n other parameters here. So now let's pick a model and try to work with it. The models for which we can do this construction exactly are models which are defined on completely connected graphs. So say that I take a generic two-body interacting problem where I have JIJs coupling the SIs and the Js. So I need to have a well-behaved thermodynamic limit and going to infinity limit. I have to think about how I should scale these JIJs, because you see here I have a double sum over indices. So naively, I could think that this double sum will give an n squared contribution to the energy. So it will make this right-hand side be order n squared. This is not totally correct for this other problem, but naively I could think that. So I have to be careful about, whether I have to normalize here the energy in a different way to kill one of these n factors, right? And to have an extensive energy that scales like n and not like n squared. Otherwise stated, each spin Si is feeling a local field on it, which I can define as, the 1/2 there, and the sum over J, which is not I, which is connected to I, of Jij times Sj. So this is the local field felt by the spin I. It's just some simple rewriting of the Hamiltonian. So say that I separate the sums. Times Si, so this is the local field, apart from the, together with the 1/2. So the fields that each spin should feel should be order 1, should be not order n. But then if I look here, I have a sum over j. So then this thing could scale with n if I'm not careful and scale the jij's in a convenient way with the number of sides in the problem. So this is just to say that for these mean field problems, one has to scale the coupling of the interactions with the system size in a special way to make the energy extensive. So let's look at the Curie-Weiss problem where the jij's are all equal to j. So the ferromagnetic problem. I can then conclude very easily that I need to scale the jij's with 1 over n to make the energy extensive, or to make the local fields be order 1. Why do I say that? Well, because you see, if I put here all the j's to be equal, and I focus on the ferromagnetic configuration where all the spins are equal to the same value 1, let's say, then I have j times 1 for all the terms in the sum, and I have a double sum here, so I could get an energy order n squared, and I don't want an energy order squared, I want an energy order n. So I have to scale jij like j over n. Okay, this is in the ferromagnetic case. In the disorder problem, which is actually the Sharrington-Kilpatrick celebrated model of spin glasses that I'm writing here, where I pick the jij's from a probability distribution, I have to scale these jij's with the square root of n instead of an n. Why? Because if I look at either the energy or the local fields, and I pay a little bit of attention to it, since I will have here a sum of spins which are not all equals to 1 in the ground state, but there will be as many 1s and minus 1s in this ground state because of the quench randomness, then the sum typically will be order square root of n, law of large numbers applied here. So square root of n over square root of n cancel, and then this local field is correctly order 1 if I scale the jij's in that way. Okay, so as in the standard Curie-Weiss problem, I have to be careful about the scaling of the jij's in the disorder case. The scaling with n is different. There is a square root of n instead of n, but okay, once I do it, I'm okay. So using this information, the probability distribution of the jij's that I have to work with, for example, is of Gaussian kind. This is a good choice because it makes calculations easy. But the variance, the sigma squared, has to be j squared, as I was saying before, divided by n. Because the jij's scale with square root of n, jij squared scales with n, 1 over. So this is the variance that I have to pick in the distribution function of the interactions when I work with fully connected problems, with two-body interactions. This is all the implications. I mean, I'm working with these other problems with two-body interactions. I'm scaling the jij's with square root of n, its variance with n, so as to have an energy of order n in the putative and plausible spin glass phase in low temperatures. Okay, there are even more generic problems with three-body interactions that we like to work with. I'll jump over this transparency. You can have a look at it if you are interested later on. The scaling with n of the interactions is different in this case, but okay, just let's focus on the two-body interacting problems. So we have now understood how to define or how to choose the probability distribution of the couplings in the case of models with fully connected interactions. Well, now we can really go and construct this landscape, complex free energy landscapes and beyond the Ginzburg-Landau paradigm. So, okay, so let me see how I presented this. Yes, so the way in which I presented this is to first recall an exercise that perhaps you have seen in the statistical physics lectures, which is how to derive this free energy landscape of Ginzburg-Landau kind from the Curie-Weiss model of ferromagnetic transition to later do the same or a very similar construction in the disorder problem. So we have defined the Curie-Weiss problem and have, in the two previous transparencies, realized that we need to normalize the coupling between the spins by n. So now the Curie-Weiss model looks like this. J is order 1. There is the 1 over n in front of the two-body interaction, and there could be an applied magnetic field, external magnetic field added to the Hamiltonian to be even more generic. So if you construct the partition function for this problem, and you introduce an auxiliary variable in the partition function, which is this u variable here, which is defined as the sum of the I of the SIs divided by n, you can transform the partition function for this Hamiltonian into an integral over this auxiliary variable of e to the minus beta n times a function, which I'm calling bold f here, of the auxiliary variable u. I can send you notes for this derivation if you don't remember how it goes. You can have a look at it in the tutorials if you wish. It's just very simple. It's just a change of variables within the partition sum from these SIs to these U's, and then you integrate you sum over the SIs, and then you get this form of the partition function. So the form that this function f in the exponential takes is this one. So there is the energetic contribution that comes from this term here that you can just read from the expression. There is this magnetic field contribution that comes from here. You see that the u is over there. And this other term, where is it coming from? This other term is an entropic contribution that comes from counting how many ways of choosing the SIs there are to get the same value of u. So it's a degeneracy that gives rise to an entropic contribution that comes from this number counting. Okay, so for example, if all the SIs are equal to 1, you have one such configuration, and this one such configuration gives you u equals to 1. But if you reverse one spin, then the sum will not be equal to 1. It will be equal to n minus 2. And then when you divide by n, you have 1 minus 2 over n. And there are n ways of getting the result, because you can turn around the first spin, turn around the second spin, turn around the third spin, and so on and so forth. You have n choices of turning around one spin. So this number has to be taken into account when you go from the sum over the SIs to the integral over the u. And this is what gives rise to this entropic contribution in the exponential form here. And it's what transforms, if you wish, the e to the minus beta h, which only had energetic contribution in the partition function, into something of exponential kind, which takes now the form of the free energy. So this is why this function in the exponential, I'm calling it f, because it's like a free energy. It has an energetic contribution in the first terms, and it has an entropic contribution in this second term. The form of this entropic contribution you can derive. I let you do it as an exercise. This is the typical entropic contribution of easing spins. If there were, other kinds of spins, not easing ones, well, the form will be different. Easing plus or minus 1. If there were, I don't know, for example, plus, minus 1, and 0 spins, then the form of the entropic contribution would be different. Anyway, so you have now transformed the partition function into this integral over u of e of minus beta n times a function f, which is a function f of a variable u, which is order 1. So you see, because I have a sum over n, but then the normalization by n here. So little u is order 1. Bold f of u is order 1. Beta is order 1, but I have an n in the exponential. So now I can claim that this integral can be evaluated by saddle point. Saddle point tells me that I have to look for the minimum of the function f of u, and this is the one that will control this integral over u. And from that saddle point, u saddle point that minimizes the function f of u, I get the actual expression for the free energy density of this problem. So the f is dominated, the actual free energy density is dominated by the saddle point evaluation of this integral over u. And the equation that gives me the saddle point, okay, I'll also leave it as an exercise, is, well, this very famous u equals tangent beta ju form, the Curie-Weiss or the mean field ferromagnetic equation. So you see, this is one way of deriving the Ginzburg-Landau form, because this function, bold f of u here, if you draw it, for temperatures below a critical temperature and for h equals to 0, will take this double well sort of form, while for temperatures above a critical temperature, we'll only have a minimum at 0, at h equals 0, right? So this function f here is the Ginzburg-Landau free energy density, and it has this simple, change of form from high temperatures to the low temperatures, from a single minimum to the two minimum situation. Well, okay, this I can jump over. This is what I'm drawing in the blackboard, and this is a way of deriving this Ginzburg-Landau sort of thing. Now, let me try to do the same or a very similar treatment of the disorder problem. So I have this Charrington-Kilpatrick model. I recall that the JIJs have zero mean and they have variance normalized with n in this way. And I may also have random fields or fields applied and added to the energy in this way. So there are different ways to treat this problem, but I will tell you one. There are more precise ways of doing it. Proceeding in a similar way to what I've done for the other problem, one can derive the equivalent of the boldface f function that will now be a function of all these local order parameters mi's and not just one, which will take a form where you have an energetic contribution coming from this term, where basically one replaces the SIs by their average. And then there's SI replaced by MI, SJ replaced by MJ. I have set this field to 0 because otherwise my equation would have been too long. So I erase this term, it's not there. And then you have the entropic contribution, which takes the same form as the one I had before, only that the M is the local one, and I need to sum over all the local terms. So this is the entropic contribution, this is the energetic contribution, and you compare to the other form I had, well, it's very similar, right? But instead of being global M's that appear, there are local M's that appear, and you have the sum over I applied to all the objects, all the terms here. From arguments a la saddle points, which are the configurations of MIs which correspond to equilibria or metastable states? Well, there will be the ensembles of MIs that render these F extreme, not necessarily minimum. Minimum would be the equivalence of this, but this is a maximum, you know, at low temperatures, if T is more than Tc. This maximum is also interesting. So what you should have to do is to look for the extremes of this function F. So you take the derivative, we're to mi, and then you derive the saddle point equations, which are very similar to the previous ones, but again, you have indices I to take care of. So these
Leticia,
have, yes.
Yeah. So earlier, this entropic part, I mean, so earlier one could think of like lots of different configurations give the same magnetization. You just count, right? But now at the local level, I mean, how does one think? Because it's looked like, and there's not much degrees of freedom.
You will see it appearing in one way of deriving this. You will see where it comes from in the next transparency. In a very simple way to derive this free energy density, where is the assumption and what is made? Yes, just give me 1 second. Okay, so you have the free energy landscape, which is given by this function f, and you can identify which are the extremes by just setting to 0 the derivative, the first derivative of this mi with respect to all the, of this f with respect to all the mi's. And you can also study the stability properties of these extremes by taking second time derivatives and computing the Hessian around these stationary points, and you can have a look and see how many directions in which it's, you know, like this, and how many directions in which they are like that, by looking at the eigenvalues of that Hessian. So let me give you a very simple way of deriving this form, and then you can see which are the assumptions. So the more simple and traditional way to derive this kind of mean field landscapes is to claim the following. So you will have a probability distribution of the full configuration of the spins that you don't know. Okay, so this is joint probability distribution of all the SIs. But let's assume that you factorize this probability distribution as a product over all the sites of the probability distribution of each site of the site you're looking at. Okay, so of course this is equal here is not exact, it's an assumption. So, okay, let's make this assumption. And let's also complete this assumption by saying that the PI of SI takes this form. Okay, so MI here is a parameter, and I'm working with these in spins. So I have delta SI1, delta SI minus 1, and all these two deltas have weights, 1 plus MI over 2, 1 minus MI over 2. This choice is motivated in 2 ways. So first thing, this PI has to be normalized to 1. So you have to check, you can do it as an exercise as well. Here. So you have to check that the sum over SI equal to plus or minus 1 of PI of SI is equal to 1. This is normalization. And you want to also satisfy that the average over PI of the field of the spin, I is equal to MI. So this is the average of the local spin, actually the average over the full probability distribution, but since you have factorized the probability distribution in this way, it's only the local PI that will appear in the average. All the other ones, because of normalization, normalize to 1, and then you require that this average be equal to MI, and this implies this condition there. You can check, so check that the form of PI of SI proposed satisfies these two conditions. Okay, so it's a simple calculation, that let the students do it. So once you have proposed this factorized form of the joint probability distribution of the spins, now you can use it to express the average free energy written in this thermodynamic way, let's say, as energy minus T entropy, where entropy is the log of the number of configurations of the SIs that you have. And I should have written instead of this thing here that the now I can erase here to have some space. So for the S, what you will do is you will write P log P. Okay. So this will be with the P given over there. So this will be your entropy, and the average of the entropy, okay, is the average over the this will be your entropy, and the average of the entropy will be the sum over the SIs, all of them, of P of the SIs log of P of the SI. Okay, now I have the P log. Okay, so this is the average of the S which appears there, and the average of H, okay, is the average of the energy that you have. So average corresponds to sum over the SIs of whatever you want to average times P. So this can be done. This calculation can be done. And when you do it, you will see that because of the M's are within the P's, and because of the log here, you will get the form that I wrote before for the entropy. So it's a calculation. Okay, I leave it again as an exercise, and I can also send notes where this is done in detail to the students if they want to have a look at them. Okay, so they're more formal, I would say, or more systematic ways of deriving this free energy density using Legendre transforms and so on. And the relevant reference is this one here. The nice way, the nice thing about these more formal ways of deriving the TAP equations is that it can be extended to other cases. So it can be extended to stochastic dynamics, it can be extended to quantum systems, can be extended in different ways. And but okay, I don't have time to discuss it, but if you're interested, again, I can give you references. In the end, of course, you end up with the same equation, but you can even control finite ending corrections and things like that. Now, I don't have a lot of time to discuss this. This is a little bit technical, but what Fowles, Anderson, and Palmer realized is that the equations that you derive with this procedure and with this assumption and these free energy density here and this equation were not completely correct. And the method of George and Yedidia captures also the correction that is missing in these equations. And let me just give you a flavor of what this correction is without going into the calculations. The calculation is in the slides, so the students can have a look at it if they're interested in. What is missing is what is called the Onsager reaction term. And to give you an idea of what it is, it has to do with the following. So I have two body connections that I'm going to represent with this sketch here. And if you look at what happens when you look at a loop where you go, you look at what happens to the spin I, and what is the effect of the spin I being magnetized on the spin J with which it is connected, So because of its magnetization, I will be applying a field on J, which will make J magnetize more than what it's already magnetized because of its connections with the other spins. So it makes J magnetize more, I would say. So then this extra magnetization of J implies a field on I itself, which makes I magnetize more. So there is a kind of, increase of magnetization of I because of its own magnetization. And this you want to eliminate. So this Onsager reaction term which is added to either the free energy and then the equations, avoids this feedback kind of mechanism here. Actually, for the Curie-Weiss problem, it's not necessary, and this is why you never heard about it probably, because of the 1/n scaling of the interactions for the ferromagnetic problem. This Onsager reaction term is killed by n, or if you wish, this mechanism is killed in the end going to infinity limit, and you don't have to care about it. But in the disorder problem, the JIJs go like, you were using a square root of n here, with these JIJs being order 1. So in this spin glass case, this Onsager reaction term is finite. It's needed to be put finite and correct the tap equations or the tap free energy with an extra term. So I understand that it's very difficult to follow what I'm saying, in words just like this. I suggest the students, if they're interested, to look at the slides. It's done carefully in the slides. And basically what I'm telling you is that the local field that the spin I should feel is not only the one naively that you would expect from the coupling between the spins, but you have to subtract something. You have to subtract this term, which is taking care of this, feedback that you would have otherwise. Is killing this feedback that you would have by these loops over the spins. One can prove that it's not necessary to worry about longer loops where you would go here, there, and then go back here, because this one is really killed by the n factor in the normalization of the JIJs. So there are no longer loops to consider, but the two-body loops, yes, you have to kill. So basically, this changes a little bit the tap equations by adding this other term. It's not a nasty term, it can be dealt with. So, it complicates a little bit the tap equations. It changes, for example, the critical temperature at which you start seeing this complex landscape appear. It's modified a little bit by the presence of this term. So it's modified in a way that this critical temperature coincides, and is the correct one that you can find with other methods like replica tricks or dynamic calculations. So it gives you the good behavior for the full system. If you were to ignore it, well, the qualitative features would be the same, but the quantitative features, like the value of the critical temperature, would be wrong. So, okay. Some people study what are called the naive tap equations without this term, and still there are interesting things coming out of their analysis. So, but still, it's not difficult to take care of this one in numerical calculations. For example, it doesn't make life more complicated. So it's better to include it. So this I can jump over that. I see that there are some questions. Okay. orders of magnitude. This is again about the Onsaga term. So let me finish with this, and then I go to the chats, and it's also late. So to summarize, the top free energy for this Sharrington-Kilpatrick model looks like this. So this is the energetic contribution. This is the Onsaga term. This is the entropy. And at low temperatures, if one looks at the structure of minima, maxima, and you will have these complex landscapes appearing. Many choices of the EMIs that give you all these stationary points that appear here. With these pictures, one has to be careful because these substrates on which the landscape is drawn is n-dimensional. So sometimes, people draw these arrows on top of the barriers to say, okay, the system to go from these states to those over there, it has to jump over the barrier. This sometimes is misleading, and one has to be careful because in this drawing, you have only one direction along which you can go from this to there. But in real life, you have n-1 directions as well, which you're not drawing in this picture. And the system could go from here to there, maybe not jumping over a barrier, but going across the mountain in a different direction. And it has many choices of directions. So activation over barriers in higher dimensional spaces, in high dimensional spaces, may not be the leading mechanism to go from one metastable state to another one and eventually to the lower lying ground states in the problem. So one has to be careful about the interpretation of these plots. But okay, these plots exist. Just remember that here there are n other dimensions which are hidden and you cannot draw them on the pictures. Okay, so the stability of the solutions of these extremization equations can be studied by looking at the Hessian, as I said already. And okay, this is the sort of sketch that people draw, and people are interested in understanding the topography of this landscape on the n-dimensional substrate because it has an impact in optimization problems where we want to find the best possible algorithm to find the minimum, which is hidden somewhere here. Absolute minimum, I mean, in this landscape. Okay, so I will stop here and go to the chat. Okay. Okay, so why is back reaction term subtracted? It is to avoid, this what I try to explain here. So it's to avoid that the magnetization of a single spin acts on itself through this loop and increases its own magnetization because of itself. Okay, so you don't want that. So what you want to know is what is the magnetization that this spin achieves because of the effect of all the other ones on itself, but not because of itself. So if you do the calculation and you see which one would be the magnetization that this spin obtains because of its own initial magnetization, you will see that it takes the form that Onsager says, and then you subtract it, and then you are okay. It's like disconnecting, what you're achieving is like you are disconnecting this spin from the rest. You are disconnecting the effect of this spin on the rest, and you're looking at only the effect that the rest has on itself by subtracting that term. What I suggest is that look at the slides, look at how it works, the calculation of the Onsager term, and then I think that you will understand why you have to subtract it. It's not very difficult. It's just a question of using susceptibilities and using linear response theory. 2D model, when quenched to zero temperature, end up in few metastable states 1/3 of the time. Yes. However, in free energy, there are no metastable states, only two minima. How do these metastable states occur then? Okay, so let me, for the other ones, give you a little bit of background, and I can explain what you are saying. So, what Rango Paul, sorry if I pronounce it not well, is referring to is that if you take the 2D Ising model and you point it to 0 temperature from a random initial condition, you will realize that with some probability, which is non-zero, P horizontal, let me call it, different from 0, P vertical, different from 0, and okay, P diagonal, different from 0. Let's take periodic boundary conditions. And the system will end up in a configuration which is like this. So this is up, this is down, this is down. So you see there are periodic boundary conditions. So this is joined here and this is joined there, and periodic boundary conditions are satisfied. And you have a band with flat interface with the rest of the system, where the system is pointing in the opposite direction to the rest. So it didn't reach equilibrium with full order. So why does the system do this? The reason is that, and what is the probability of horizontal, with I'm highlighting here, to reach this kind of configuration? There will be vertical, and there will be other possibilities as well, diagonal, and that, and so on. So the reason is that this is something on which I worked as well. So the thing is that very quickly, in time scales with a scale with n in some way, but rather quickly, the system goes to a critical percolation situation or configuration. And in critical percolation, you have a certain probability, pH, which is known exactly, of having configurations where you have percolation along the horizontal direction. And you also have analytical results for vertical, okay, by symmetry, these are the same, and for the other cases. So very quickly, rather quickly, let's put it this way. So in a time scale for percolation that depends on system size, but not as L to the Z with another power, the system goes to this critical percolation situation, and the probability of percolating horizontally, and then you know which is the proportion of initial conditions that will end up in this configuration here. So this is something on which Redner has worked in the past, Sid Redner, and Marco Pico and myself and other people have also worked. Now, so this is peculiar of 2D, and it's also peculiar of t equals 0, because this flat interface is fully stable at t equals 0. Once it's built, you cannot kill it. So the percolating configuration that you get at this time, T percolation of L, will have some rough interface, will be something, I don't know, I'm just drawing something like this. The evolution, what it will do, as I was telling you, is that by this curvature-driven mechanism, will make this interface flat, but it will not kill it once the critical percolation configuration has been achieved. So in the course of time, it will just render it flatter and flatter until the completely flat interface is built. And once it's built, it remains. At finite temperature, well, there will be a fluctuation that will move a little bit, start moving and diffusing these interfaces, and then the interfaces eventually they will meet, and the system will manage to go to the final state. But it's especially of t equals 0 that this is perfectly stable and it remains this way. Now, okay, this is what is going on. I mean, this is what is going on, and now it's understood from actually the first papers of Renner and company were just signaling that, okay, there's a proportion of configurations that don't reach full order. How is it so? And then we understood this story of the percolation phenomenon, and okay, we understood. I mean, and they understood as well how this thing goes. Now, okay, so now the question was, how do I understand this from the point of view of the Ginzburg-Landau free energy landscape? And so what I would say is that in the Ginzburg-Landau free energy landscape, initially you're here. Okay, because initially you are at 0 order parameter, this is the order parameter, so you start from a configuration over there. And to fall from this maximum, you need some, fluctuations, you need some thermal fluctuations, you need something to push, or fluctuations in the initial state, or thermal fluctuations on top of the initial state. And I would say that the configurations that end up in these, situations where you don't kill this interface, well, somehow they don't manage to fall from there. They fall a little bit, but they don't fall completely. This is what I would say. So in this picture, it's true that you don't see these other metastable states appearing, but it's also true that you are condensing everything that is going on in a single order parameter. And still in the in this ferromagnetic problem, well, there are other things going on as well. I mean, this is a global order parameter, and you are not taking into account other possible directions that in general are not important, but they may be important for some things. So again, this is what I could say about this question, but this is a very good question. Yes. Okay.
Let's I had a question. So for the SK model, the Sherrington-Kirkpatrick model, if one did the replica calculation,
yes,
does one, so for the free energy, does one get this on-Sager correction eventually?
No, you don't see it in this way, but what you really, the way to convince yourself that the on-Sager correction is necessary is that you do so with the replica calculation on a scale, you get a TC of J, which if you normalize things in some ways with the halves and so on, is equal to J. So let's say that, with the normalization that you choose is equal to J. With the tap, without on-Sager, you look at TC of J, and it's equal to twice J. And if you do tap with on-Sager, you get TC of J equal to J. So this is one way to convince yourself that the on-Sager was necessary in the tap formalism. In the replica, you don't see it appearing.
But it's included somehow.
Sorry?
It's somehow included. I mean,
it's included, right? It's included. Yes. And then there are all other properties, but this is the more clear one. Yeah. Okay. If not, what I can do is, okay, I close here. And okay, I went more slowly than what I expected. So what I'm going to do tomorrow is wrap up the part on the quench randomness, and I probably say a couple of words about active matter. If I hope I have time, because I think it's interesting, and there is a lot of activity around those problems as well.
And Leticia, you will not cover the Martin-Segeros that you mentioned today?
But the problem is it takes long to do it.
That's all right. I just...
Yeah, it's a bit technical, and I could do it. I mean, as you prefer. I could not talk about active matter and explain the Martin-Segeros if you prefer.
Okay, it's about other people who are maybe people are interested more in the active matter. Maybe
I don't know. It's just, send me by email your opinion, and then I do as you prefer.
But just as a question, in case you don't cover, so in the Martin-Segeros, you will have some kind of microscopic dynamics through which you could go to the action by course creation?
Yeah, so what you do is you propose your microscopic dynamics, and typically you propose Langevin dynamics because, okay, your system is coupled to a bath, so you have to have noise and dissipation and so on. So first thing you have to do to write the Langevin dynamics is to go from Ising spins, which are difficult to deal with. I mean, you cannot write the Langevin dynamics for them, to what are called soft spins. So you basically put on each of the spins a double well potential, which favors plus or minus 1, but you let them be real variables. So then you can write, differential equations for the evolution of the real variables. So you go from Ising to soft by writing this, minus 1, 1. Then you do Langevin. And then you write the generating functional of this stochastic process with this Martin-Segeros procedure. And then from that generating functional, you can manipulate it a little bit, sort of in the way that we were using, well, here, still. Sort of in the way you're using here. So you have a generating functional that you manipulate to write as the integral over auxiliary variables of e to the minus n, an action on these auxiliary variables. Only that the auxiliary variables in a dynamical problem will depend on times. And so the relevant ones will be correlation functions and linear response functions. So they are like the other parameters for your dynamic evolution, both correlations and linear responses. And you have to work with the two of them because they are not related by FDT when you are out of equilibrium. So they are independent out of equilibrium. So you have to keep both. And this is what the Martin-Segeros procedure does very naturally. And then you have e to the minus n times some action of these auxiliary functions, and then you do saddle point and you derive the Schwinger-Dyson equations. This is basically the path.
Okay, thanks. But this step from Ising to soft, is it done bit like a hand waving way, or you do it?
Yes. It's just you propose it and you do it. And otherwise, instead of soft, what we like to do is to work with spherical.
With the spherical model?
Yes.
Okay.
Yes. Okay. So that's the other way to go to real variables and be able to write Langevin equations. Yes.
Okay. Thank you.
You're welcome.
Okay. So so maybe we stop for today.
Okay. Thank you. I guess the students must be very tired with all the lectures they have.
Yeah. Okay. Thanks. See you tomorrow.
See you tomorrow. Thank you very much. Bye-bye.
Bye.